Okay, here goes part 3. We're on page 165 looking at number 54. 54 shows this type of situation where it's a baseball being hit, and it shows that if it's hit at 30 degrees and if it's hit at 60 degrees, it ends up landing in the same spot, which is true. It turns out that if we neglect air resistance, which we are doing for all of these questions, the angle at which you should hit or throw something to maximize the distance that it goes is 45 degrees. So 45 degrees might look something like that. And notice how 30 and 60 are both 15 degrees away from 45, so they end up landing in the same spot. Interesting. Or having the same range, we can say. So let's see, I cannot erase that, so let's see if, well, alright, whatever. So, it asks us two baseballs in this figure were hit with the same speed of 25 meters per second. Draw separate graphs of y versus t and x versus t for each ball. So, B has more horizontal velocity, less vertical velocity. A has more vertical velocity and less horizontal velocity. So B is in the air for less time and is going to the side faster. A is in the air for more time and is going to the side slower. So when we look at, this is height versus time, or y versus x. Notice how B goes to less height, and B is in the air for less time. A is in the air for more time. The horizontal positions, I forgot to draw on these solutions. So if we were looking at horizontal versus vertical, they end up going the same horizontal distance, but A is going slower. So A might look something like this, where B would look something like this. Okay, so notice how the slope of B is steeper and the slope of A is less steep, meaning less horizontal velocity, more horizontal velocity, but notice how they end up at the same horizontal position after some amount of time. Alright, 55. Whoa, hey there. 55. Swimming, you took a running leap off a high diving platform. You are running at 2.8 meters per second and hit the water 2.6 seconds later. How high was the platform and how far from the edge of the platform did you hit the water? Ignore air resistance. So here's our situation. Moving horizontally with this speed, so not in the vertical not up or down. And in the air for this amount of time, so this is the time to fall, which we will use first. We're looking for how high and how far we go. So using again this equation for the vertical motion and knowing that our initial height or initial vertical position is unknown, this is our variable. Our initial velocity in the vertical direction is 0. Our time in the air is 2.6 seconds. And our final position, because we're landing here, final height is 0. So solving for d sub I, or original height, we get 33.1 meters. For the horizontal motion, we know that we have a horizontal velocity of 2.8 meters per second. Notice how that was not the initial velocity in the vertical direction. That is in the horizontal direction. The time in the air is 2.6 seconds, and multiplying gives a horizontal distance traveled of 7.3 meters. Next question. Okay, 56. Whew. Oh yeah, this one's a challenge. 56 says, archery. An arrow is shot at 30 degrees above the horizontal. Its velocity is 49 meters per second, and it hits the target. What is the maximum height the arrow will attain? And the target is at the same height from which the arrow is shot. How far away is it? So, in all the questions we've done so far, the initial and final heights are the same, and that makes this quadratic easy to solve. So we're looking for how far does it go, the range, and how high does it go, the maximum height. First thing we're going to do is take the velocity and break it into horizontal and vertical components. So where is that? Yes. Right here, 49 meters per second, and it's going this fast in the horizontal direction and this fast in the vertical direction. So we're describing this motion in terms of two separate motions. Using our SOHCAHTOA skills, we get this for the vertical velocity and this for the horizontal velocity, and watch where we use those. So let's see, for vertical stuff, alright, so this is sort of a trick here. So because that's a trick, let me show you this first, because I know that we have done this in class. For the vertical motion, we know that the final height and the initial height are the same, so we set those both as 0. Initial height, final height. We know that the acceleration is negative 9.8, and we know that the initial velocity in the vertical direction is not 49, not 0, it's not being dropped, it is this that we just solved for, 24.5. Solving, we have 0 on one side, we factor out a t, and we get two values. Notice how this corresponds to the initial time when it starts, and then the final time when it ends. So, given this information, we can, as long as the initial and final heights are the same, we can say that halfway through the flight, so if this is 0 and this is 5, we can kind of assume, we can definitely assume that this, the time to maximum height, is 2.5 seconds. That only works, it only works if the initial and final heights are the same. So, using this information, we could say time to maximum height is 2.5 seconds. Using, this isn't really a trick, you have seen this equation before, but this is relating velocity and acceleration and time. So, in the vertical direction, we know that it starts upward with the speed of 24.5 meters per second, and the acceleration tells us it's going to lose 9.8 of those every second. So substituting in initial velocity, acceleration, time, and final velocity, this is the vertical velocity at the top of its flight. So right here, it's not moving up or down for an instant, its vertical velocity is 0. Solving gives us the same thing, t equals 2.5 seconds. So it's kind of comforting to know that we can solve for the time to maximum height in two different ways. You don't have to do both. But given that information, substituting in is going to give us a final position or final height of 30.6 meters. So this is vertical motion, okay? We have acceleration, we have time to max height, initial vertical velocity, and this is final vertical height, meaning what is the vertical position right here. Okay. Whoops, so our maximum height ends up being 30.6 meters. And to find the horizontal distance traveled, notice how we're using the horizontal component of velocity and our time in air. This is not the time to maximum height, this is the time in the air. Multiplying yields the range. Okay, I'm going to pause here before moving on to number 57, and we'll do that as part 4.